So in the third of these thermodynamics videos, what we're going to do is put together all those energy changes we've just been looking at in order to try to calculate the lattice enthalpy, so the strength of the ionic bonds in a lattice. And we're going to do that using something called Born-Haber cycles. Born-Haber cycles put together a series of enthalpy changes in a cycle and allow us to find an unknown. So each step in this cycle is going to represent a single enthalpy change, so not multiple things, just one thing's going to happen. And all the steps must show the right number of atoms. So each step is going to be one enthalpy change, and steps are going to have state symbols. That's probably one of the most important things that you must remember and people forget, is that they have to put state symbols. It might be worth going to the front cover of this pack and writing in massive letters state symbols across the front, because that's one of the most important things about this topic. You have to have the right number of atoms as well, so we're going to make sure we do some good balancing. Now the rule is you're supposed to start from the elements in their standard states and work round. There can be easier ways to approach it than that, so we'll talk about different ways to have a look at it. We're going to remember from all those lists that we've been writing as we've gone through in the second lesson, endothermic changes, which are positive ones, positive arrows point up, exo, the negative ones, point down. And we're going to go either the direct route or the indirect route using Hess's law, and we're going to see what our values come out like. So we're going to try this. I don't want you to be too overwhelmed with this first example, because it can be a bit scary at first, but once you see a few of these, they're not as scary as they look. So we're going to try and do a Born-Haber cycle for sodium chloride. Now, the rule is you're supposed to start at 0, which we can see here on the left-hand side, with the elements in their standard states. So we're supposed to start here with the elements that make up sodium chloride in their standard states. Na, chlorine is Cl2. That's sodium and chlorine in their standard states. Their state symbols are solid and gas, but they don't actually balance for the numbers that we need. So I'm going to now need to squeeze in, bring out a little bit of space there, didn't give myself very much space, a half there, because in sodium chloride there's only one Cl. So I've got the correct numbers of the elements that make up sodium chloride. Now that is where theoretically you should start, at the elements, but you won't see this 0 on most Born-Haber cycles. So one of the easier things to remember is that very bottom line, at the very bottom, that is where you're going to put your ionic lattice, NaCl solid. Now one of the things we've got to do in this cycle is work our way around from the elements, which we've put here on the 0 line, and we're going to go all the way around to the ions. So when I would go through this with a student, I would always say put the solid ionic lattice at the bottom, and on the left, on the first line, put the elements in their standard states, and on the right, on the line that you've got, put the ions that you've got in the gaseous state. So the ions we've got are sodium ions and chloride ions, one of each. So I've put the elements and the ions that make up the solid sodium chloride. So from the elements in their standard states, we've got to convert the elements in their standard states to the ions in their gaseous states, a series of steps at a time. And you've got to think, all those processes that we just talked about, which one will I need to do in order to convert sodium solid to sodium ions gas, and chlorine, half a chlorine molecule gas, to chloride ions gas. And it's helpful to remember a sort of order, and the order that you can always do and get these questions right is atomize, atomize, ionize, and then electron affinity. So we're going to atomize the solid metal, then we're going to atomize the non-metal, then we're going to ionize the thing that needs to become a positive ion, and then we're going to do electron affinity to the thing that needs to become a negative ion. Now if a lot of those words seem unfamiliar, you need to go back to lesson 2 and go through those definitions again. Atomize, atomize, ionize, electron affinity. So we're going to go one thing at a time. I'm going to atomize sodium. So I'm going to take the sodium that's this sodium here, and I'm going to change just that, one enthalpy change at a time. I'm going to change that, atomising. The definition says when 1 mole of gaseous atoms are formed from the element in their standard state. So I'm only changing sodium, so I'm going to leave the half a Cl2 gas alone. I haven't done anything to that. So this process here is the standard enthalpy of atomisation of sodium. And if I'm given a value for that in a table of data, I'll be able to put that value next to that arrow. We won't find ourselves writing all these symbols out all the time, we'll be putting values. So I'm going to atomise the metal. The next thing I'm going to do is I'm going to atomise the non-metal. So I'm going to change this into something else. So I'm going to leave the sodium as it is, one thing at a time. So sodium is exactly the same as it was, sodium gas. But if I atomise, which is when 1 mole of gaseous atoms, 1 Cl gas, is formed from the element in its standard state, then that equation there is the enthalpy of atomisation of chlorine, when 1 mole of Cl gas atoms are formed from the element in the standard state. So I've atomised the metal, I've atomised the non-metal, had to do those two processes very early on, because the next thing I want to do is I want to ionise, and if you remember the definition for ionisation energy, it has to be gaseous atoms, so I needed to atomise before I could do ionise. So what I'm going to do now is I'm going to go back to the sodium, and we're going to change the sodium into sodium plus gas. When I do that, a mole of electrons comes off. Now, don't forget the electrons. I'm going to highlight those electrons because they're the often missed out little bit. Don't forget those electrons. This is the enthalpy of ionisation. First ionisation, I think we wrote IE1 of sodium. I haven't done anything to the chlorine atoms, so they're just staying as they are. So I changed the sodium into Na plus an electron, didn't change the chlorine this time. And now I'm going to change the chlorine atoms into chloride ions by joining the electron. The electron affinity is to join these two together and make a chloride ion, and that's going to be the enthalpy of electron affinity of chlorine. And I've turned chlorine atoms into chloride ions. And we've gone all the way around from elements to ions so that we can find out this value, and this value is forming the lattice from the ions. So this is the enthalpy of lattice formation of sodium chloride. And this value over here was the enthalpy of formation. This one was just the enthalpy of formation of sodium chloride and not lattice formation, just formation. Now we need to apply Hess's law. So it looks big, it looks a bit scary, there's lots of information on there. I'm going to use Hess's law to say that the direct route, and if we look at this, the direct route from the elements, let's get a different colour pen, that's our direct route from the elements to the lattice is just equal to delta HF, that's our direct. It's going to equal our indirect route, which is our long way round, and our long way round starts at the same place, and we're going to go from this same line all the way around. So we're going to go up all the way to the top and then down all the way to the bottom. That's going to be our indirect route, starting at the same place, ending at the same place, but going the long way around. And we're going to add up all the changes. So we go that long way around, we've got the enthalpy of atomisation of sodium and the enthalpy of atomisation of chlorine and the enthalpy first ionisation of sodium and the electron affinity of of chlorine, and then the lattice formation of sodium chloride. So we're going the direct route equals the indirect route. What if you are a bit more spatial and you look at that, you could say that the arrows that, if you imagine the centre of this cycle as being the centre of a clock, then the arrows which are moving around the clock in a clockwise direction, which is basically all of my indirect, equal the arrows that are moving in an anti-clockwise direction. So people often say the anti-clockwise arrows equal the clockwise arrows. That's another way to look at this. So I'm going to make another video to have a look at some other examples. You need to just have a little sit and go over this particular example for a bit of time. Make sure you understand where each process has happened. Go back over the previous pages and check out those definitions of all of these enthalpy changes and check you understand how they've fitted together here.